I will begin with a word of prayer. I get up here. Dear Father, we thank you for this day, and I thank you for this class and your creation. Help us to understand a little bit more about it, and help us to glorify you, what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so lest I forget, here is the exciting attendance sheet. There you go. And so today, I want to try to explain the concept of mutual inductance rather. And because in some sense, mutual inductance is probably more important than self-inductance. Like mutual inductance is the principle behind all kinds of various technologies. Like your book points out, like it's how you charge batteries without making like a physical connection in the sense of like a wire, right? You can just use the concept of mutual inductance to charge one coil from changing magnetic field in another one. So let me walk through the basic setup here. So so what we have is two coils, all right, coil 1 and coil 2. And so I'll draw the picture like this. All right. So here's coil 1. And then around that, hold on a second, make sure I don't have them backwards. No. So, sorry, my making sure I'm not misinterpreting the picture here. Somewhere tell me which one's the outer and which one's the inner book. Let's see here. Well, I guess it may not matter, because the book at least is never actually confessing which one's the outer and which one's the inner. And it is true, right, if you think about this, right? So we've got an outer coil here. So coil 2. That, if you can imagine this, if we ran a current through coil 1, right? That does put a magnetic flux through coil 2, right? And it's also true, if we ran a current through coil 2, we put a magnetic flux through coil 1, right? This is why the book statement is completely unhelpful to me figuring out which one's inside and which one's outside, because that's all the book says. Okay, because it's true of both, but anyway. So let's work through it here. So the voltage in coil 2 is equal to minus N2 d phi b 2 dt, right? And let's see here. He says that N2 phi b2 is equal to M21 times I1. M21. So this is the so-called mutual inductance. right? Now we can write down the same kind of equations, but the other way, right? I mean, it's also true. Let's see here. Well, let me get to the point. So this implies what? So we do what? Minus ddt of what? Let's say n2 phi b2, right? Pull the n inside, but then this is that, right? So what do we have? We have the time derivative of the mutual inductance M21 times I1, all right? And then assuming that the mutual inductance is constant, and that's a reasonable assumption because it's just based on the particular geometry of the coils and everything here, then we have M21 with a minus, I'll pull the minus out, di1 dt. So you can compare this. Remember what we derived for the self-inductance? What was it for the self-inductance? What was the deal? We had E was what? Equal to L di dt. Remember that? That's the voltage for. So compare, and I think there's a minus 2 here as well. All right. So you can compare that to this, right? But what's the difference in this story? Here. This was the inductance of a coil. This was the current flowing through the same coil, right? Whereas now we're talking about the voltage induced in the outer coil to the change, related to the change in current in the inner coil. See that? So this is why it's mutual inductance. There's no actual there doesn't actually have to be an actual wire connecting these. These can be, isolated by an insulating air gap, and still you can generate voltage in the outer coil due to a change in current in the inner coil. This is very cool. Now, we could also symmetrically write the equation, changing the story, flipping the script. We could also talk about E1 being equal to minus N1 times the magnetic flux rate of change in the first coil, d phi b1 dt, right? And we could say, well, N1 times phi b1, we're going to define that's equal to M, this time 1, 2, times I2. So just, full disclosure here, these are definitions. This is the definition of the mutual inductance, okay? Definition. Again, this is a definition. What we're defining is the M12, okay? And then go through basically the same calculation, and we'll get what? We get minus M12 di2 dt. Right? So long story short, this is equation 30.5 in your textbook. They tell us that the mutual inductance of coils 1 and 2 we're just going to call M. And on the one hand, it's N2 times the flux through the second coil divided by the current in the first coil. But you could also calculate the mutual inductance by N1 times the flux through the first coil divided by the current through the second coil. All right? So let's work out an example with some numbers in it. So here's an example. And I'm going to be super boring and just work the example in the book if you guys don't mind. So here we have a Tesla coil, which is no relation. This book was written before that. From a Tesla coil, high voltage, blah, 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 blah. Popular in science museums. Okay, great. A long solenoid with length L and cross-sectional area A. Closely wound N turns. Let me draw the picture here. So we've got this coil. All right. And this distance is L. And then, so I'm going to use some color coding. This is N1 turns. All right. And then we've got another coil around it with N2 turns. I'll use red, I guess. Yeah, blue. So all right. Don't think too much about my my picture here. N2. All right. Okay. So the cross-sectional area of the big one is A, not the long turn. The cross-sectional area is A, I think is what it says. Yeah. So let's see here. So this right here, area A. Then the question is, what's the mutual inductance of such a situation here, right? So here's what he says. He says, let's see here. So you guys help me out. What is, if we have current 1, I need another color. Suppose we have current 1 flowing through the first coil, right? What then is what's the magnetic flux due to that current inside the coil here? What is it? We should do what? A times B1, right? Which is what? What was the magnetic field due to a solenoid tightly wound? Do you guys remember? It was mu naught N1 I1. What was the little N1 and what's the little I1? Here, what is N1? N1, remember, is the number density. So it is literally big N1 divided by L. Yeah? So this is like A mu naught big N1 I1 divided by little l. That's phi B1. And let's see here. So to calculate, so we can do that. What would the magnetic, what would the flux through, what would the flux through the second coil be? So he's going to use this formula here to calculate the mutual inductance. M is equal to, let's see which way we're going to go. N phi B2, I guess. Now there's a little bit of a trick here. So it's supposed to be N2, phi B2 divided by I1, right? So what would the flux be through the second coil if the current I1 is flowing through the first one? We don't know I2. I mean I2 we can just assume is 0. So, I mean, more to, well, so notice that that is equal to, and you guys maybe can explain this to me, N2 equal to N2 times B1A. Now, why would the flux through the second one be the first magnetic field times A? Why would that be the case? Like, if you think about the bigger coil, right? All of the flux is coming from what? Just where it's inside the inside coil, right? So the magnetic field due to current 1 is essentially 0 outside the very long coil if we're in the middle, which is the situation in the example. So essentially all of the magnetic field lines are just from this inner core. So the flux through the blue coil, despite the fact that it's bigger than the inner coil, is still the same as the flux through the inner coil, which is why I just do B1 times A here. But then we have the formula for the flux. Well, we can solve this for B1, right? I mean, I should have really solved this for B1. The book has just solved for B1. So B1 is what? Mu naught big N1 I1 divided by L, right? So there's that. We plug that up in here, what do we get? N2 times, oh man, I had B1A, I should have just left it. Wait a minute. Well, A does matter, doesn't it? Okay, fine. I guess I'm back to here again. That was dumb. So A mu naught N1 I1 divided by Li1. Therefore, mutual inductance is what? Mu naught N1 N2 times the cross-sectional area of the inner coil divided by L. So like, let's build off this example. What if, hypothetical, let's say example 2. What if your inner coil had, let's say, 1,000 turns, and your outer loop had, say, 20 turns, and let us suppose that the cross-sectional area was like, oh, I don't know, 4.0 centimeters squared, right? And let's make the length of the inductor, say, 5 centimeters. Find the mutual inductance in this case. What would it be? So we can work it out, right? 4 pi times 10 to the minus 12th. Is that right? Did I remember that right? Minus 7? Okay. Yeah, don't trust me. I have brain damage from answering student questions today. 20. The area, 4 point. I should have given us a radius. That would have felt more, How many, 4 centimeters squared is what? Converting that to meters, what do we got? Right, so 1 meter is 100 centimeters, so when I convert I get, what did you say? 0.0004 meters squared. Well, I'm not going to put the meters squared, but that's in meters squared. And then divide by 0.05 meters. I'm not going to put the meters because I'm saving all of the units for the one that I'm interested in, which is Henry. Okay, so henries. Also the units for mutual inductance. Inductance, mutual inductance, same, same dimension. All right, so what do we got? Oh, well, I am getting, well, that's kind of cool. That's actually a somewhat reasonable number here. So 2.011 millihenries. All right. Yeah.
Doesn't this solenoid not have enough length to where we can reasonably make the assumption that would require that equation to work? Doesn't the length need to be fairly big compared to the cross section?
Oh man, did I make unreasonable? Let's see here. How can I fix that?
Is that about, I don't know.
Just a second here. Oh, I don't know of any nice way of fixing that. But yes, maybe fair enough, but perhaps I am violating the terms of the agreement of the calculation, right? Like, is it fair to say that the length of 5 centimeters is long? I think that's pretty long for 1,000 turns, though. I mean, I don't know. Anyway, this is the best we can do in this course at the moment. Like, I don't have more sophisticated formulas for. And I am assuming that the other coil is in the middle, like in the, well, kind of like in my picture, but, So, all right. Let's look at these equations. What do we have? We have, so listen, the thing is, you're like, well, what about the current in the second coil? This is the thing. To figure out mutual inductance, you imagine a current in one of the coils, but not in the other, and then you figure out how the fluxes are related. Because of the symmetry of the problem, it's equivalent. Like, we would have come to the same conclusions if we had imagined the current going through the outer coil, but then we can't do that because we don't have the physically simplifying assumptions in that case, so we don't want to do that. So I guess there's a lack of symmetry in that regard. But anyway, you imagine the current going through one of the coils, and that helps you to figure out what the mutual inductance is. Once you know that, then you can use it. So actually, it is true that if a current is changing, if there's a current going through one of the coils and is changing, it is going to induce, right, through Faraday's law, a changing current in the other coil. There's going to be an induced current. All right, so it's like, it's right for it to bother you for me to say, well, the current's just non-zero in the one coil, but it's not in the other, because that's not the physical situation once they're changing. Nevertheless, we can consider a constant current in order to figure out what the mutual inductance is. But once we figure that out, we're actually thinking about changing currents, truth be told. And something very interesting happens if we relate these formulas all together. Like, how is E1 and E2 related? So you guys help me out. Let's relate E1 and E2. How are they related? Let's write it down. We got what? On the one hand, we have E1 is what? How did it go? It was minus minus m di2 dt. And E2 was what? Minus m di1 dt, right? So what does this tell us? I mean, we can solve for m, right? M is equal to what? We'll solve for minus m, you know. Minus m is equal to E1 divided by di2 dt, but it's also equal to what? E2 divided by di1 dt, right? So that means that there's a relation between the voltage and the current in the one coil and the other, right? Like, I can rewrite this. It says what, like E1 times di1 dt is equal to E2 times di2 dt, apparently. All right. So example 30.2 here. We have well, in example 30.1, they give some numbers that makes this work out to 25 microhenries. All right, so I didn't finish example 30.1. I made up my own end to it. Sorry about that. But so here, well, I'm gonna call this. I'm gonna put some quotes around here. But the idea is to give a. Oh, fine. I'll make up my mind eventually, guys. Sorry. So we're given that I2 is equal to 2.0 times 10 to the 6th amps over seconds times time. So they give us current 2 as a function of time. And then they have at A, at t equals to 3.0 microseconds, what is the average magnetic flux through each turn in coil 1 due to the current in the outer coil. And then part B, what's the induced EMF? All right. So we'll finish. We'll stick with the book's numbers. So the book gave physical parameters to, the end of 30.1. They have that the mutual inductance is 25 microfarads. Farads. Listen to me. That's not a good sign. I told you guys I'm brain dead today. Microhenries from end of example 30.1. So that is assuming that the length is 50 centimeters, the area is 10 centimeters squared, and the number of turns is 1,000, and the number of whoa! I just made that up. I am almost identical to the book. I shouldn't tell you this, but I didn't read this example before class. That makes it more impressive, right? That the numbers are the same. But I mean, I read it before. I've been studying this all day. Actually, it was impossible because I've been busy doing students' homework all day to prepare for class. But and next semester, when I do away with office hours, that'll fix it. So anyway. So the question then is, how can we figure out the average magnetic flux in coil 1? How do I figure that out? coil, so I want phi B1. I think that would just be phi B1, which we can get from, how's that go? Somewhere on these boards is the right equation. So we just need the, wait, what? Dudes. No. Uh-uh. Uh-uh.
I didn't see that.
Yeah, this is a 1. 1 and 1. 2 and 2. All right. Yeah. 1 and 1. All right. Okay. So that matters now. That matters actually quite a bit right now. So phi B1 is M12 times I2 divided by N1. What did I just say? I can't remember. My brain not working. So I need the mutual inductance times the second current times the second current divided by the number in the first coil, right? All right, so for the book, this is 25 microhenries times the, now at 3 seconds, at t equals to 3 seconds, we've got what? 2.0 times 10 to the minus 6th amps per second times 3 times 10 to the minus 6 seconds. That gives me my current. And then divided by N1, which was given to us in the previous example to be 1,000 turns. And so what do we got? .25 times 6 divided by, yeah. So that gives us 1.5 times 10 to the minus 7 Tesla meters squared. Now Tesla meters squared actually has a name. I don't know if I've mentioned this in here yet or not. I mentioned it I at least mentioned it in the problem session. Maybe I didn't mention it in here. But a Tesla meter squared is also known as a Weber, or WB, a Weber. A Weber. Which is kind of, I mean, I don't know, it's kind of funny, right? We don't have any, as far as I know, well, do you guys know? Is there a name for electric flux? Like a set-aside unit for a, you know, Newton per Coulomb times meter squared? Yeah, I mean, we don't even have, like the electric field doesn't even have its own like dedicated unit, right? Like what's the units for magnetic field? Teslas, right? So important that we've made a whole company and, you know, out of that. There's no hope for the electric field. It doesn't even have a proper name for its units. Yeah. Oh, you're going to talk about the, okay, go on. A negative? Oh, yeah, that's supposed to be 10 to the plus 6 there. That matters because those cancel out and give you a 6, which gives us this. Yeah. Okay, so that's the answer to part A. How about part B? We want to find the induced EMF. So, like, what's E1? It's what? Minus M di2 dt, right? Which, oh no, I think it's this. Yeah. So, and that's 25 times 10 to the minus 6th. That's my microhenries. And then my di2 dt, what is di2 dt here? It's just 2.0 times 10 to the 6th, right? And that's all going to have units of volts. So the 10 to the 6th and 10 to the minus 6 cancel, and we get minus 50 volts. I hope. Whew, that's a relief. All right. So this is mutual inductance. But this is, there's more to mutual inductance than this. It's bugging me. They're burying the lead. What makes mutual inductance really interesting is what? Charging your phone is not that's one thing. Like, yeah, charging pads, sure. That would be one example. But how? All right, well, I'll have to talk about it another day, I guess. But when I think about mutual inductance, I think about transformers. All right? So like transformers are exactly this kind of thing. You have one coil wrapped around another, and you're able to multiply the voltage from one coil to another using this scheme. That's actually really important because it's central to how we distribute power, for example. Ohmic losses in power lines are like I squared times R, right? So the square of your current times the resistance gives you the power that you're losing per unit length, basically, right? So if you have a large amperage, you've got a lot of power loss. On the other hand, if you have a small amperage, you have a much smaller loss. Now what's the trouble? The power is the current times the voltage, right? So if you want to have a given power, you've got two options. If you want to have a large power, right, you either have to have a stupidly large voltage and a small current, right? Or you could have a stupidly large current and a small voltage. They each have their advantages, right? So the stupidly large voltage is a problem because then you have this thing called, dielectric breakdown, which is when, there's a direct arc from one conductor to the other, right? So like the really high tension power lines, you'll see that the different, different wires, different parts of the circuit are separated not just by a foot or something, not by some, insulator wrapped in a coil or something. They're literally separated by several meters, right? To have that giant air gap, and they use glass things to hang them off. So they're isolated electrically. So that, allows you to have a potential difference of a couple 100,000 or even maybe a quarter million, 750,000 volts between those very high power lines coming out of the power generating stations, right? So we transmit power at 1 million volts, 500,000 volts, something like that, for long cross-state distances. And then once you get to a locality, you then transform those voltages down, right, to a couple thousand volts, and then you send the couple thousand volts out to your different, neighborhoods. And then in each neighborhood, you'll see a transformer which takes the couple thousand volts and transforms it down to the line voltage that we use in the US of 110 volts AC. The reason this is done is at every stage you have a much smaller current than you would otherwise, which means you're not losing power to the, the ohmic losses of the power distribution. That in a nutshell is why transformers are so important, because they allow you to easily and with fairly little loss step up and down from one voltage to another. And we can derive that from mutual inductance, but I don't see how to do it today, which is bothering me. And it's not in the book, which is annoying. Why is that not there? Come on. It must be more complicated than I think. I remember this from community college. I have a 2-year degree in electronics, and so we're taught things there as if they're just easy, right? But it's always like the devil's in the details, and I wasn't shown sometimes the derivation's hidden or something. But maybe it's simple, and maybe I just don't see it at the moment. We'll find out. But anyway, that's why mutual inductance is important, because it's the basis for transformers. And besides being a, somewhat predictable and kind of overused IP, it's also a very important technology.
I heard Transformers 1 was good.
Transformers 1 was good? Yeah, Transformers 1 was from a different time. Yeah. Before that actor got kind of crazy, but anyway.
Transformers 1 that came out this year.
Oh, this year. I don't pay. I mean, the only movies that come out in the last couple of years have been Dune.
Really?
So, I mean, that's all that.
Is M12 and M21 the same thing?
Yes, M12 is equal to M21. That is true. Yes. So that's why we just call it M. So anyway. Anyway, so that's it for today, guys. I'll stop here before I do something horrible.